Okay, introduction to gas exchange. Okay, so two important things has to happen. Okay, you guys know the first one, which is the body has to get oxygen. But what you don't know is the body also needs to get rid of carbon dioxide. Both are toxic. Okay, and both are important. So hypoxia is too little oxygen. Hypercapnia is too little. Too little bit of carbon dioxide, so too much carbon dioxide. Okay, so to avoid hypoxia and hypercapnia, okay, the body needs to respond to three separate variables. Okay, oxygen, carbon dioxide, and the last one is actually really important, and that's pH. Okay. Okay, so this you should already know. So these definitions you should definitely know. Okay, so make sure you know these definitions. Okay. You don't need to know these numbers exactly, but you should know roughly what they are, especially the pH. Okay. Okay. So breathing is the bulk flow of air into and out of the lungs. Okay. So there has to be gas exchange in a couple of different places, and gases always follow the law of mass action. Okay, so higher concentration to lower concentration. So the PO2 of alveolar air goes to the PO2 is greater than the partial pressure of the O2 in the blood. So air will enter into the blood. Okay, the PCO2 of the blood is greater than PCO2 of alveolar air. So CO2 will leave the blood and go into the alveoli. And this is the same as in the tissues. Okay, so the PO2 of the blood has to be higher in the tissue for the gas to go into the tissue. Okay, all right. So, okay. So lower alveolar pressure of oxygen decreases oxygen uptake. Okay. There's two ways to do that. One, the minor way is the first way, which is the composition of expired air. Well, if you're in Denver or you're on Mount Everest, there's less PO2 in the atmosphere. The pressure is less, so there's less oxygen in the atmosphere, and therefore it's harder to breathe. Okay. All right. Alveolar ventilation is the primary one. Okay, there's low oxygen if the ventilation is inadequate. Okay, hypoventilation. Okay, this happens one of three ways. Okay, one, decreased lung compliance. Compliance is the ability of your lungs to stretch and open. If you can't open up your lungs, you can't breathe. Okay, you can't exchange air. Okay, second is increased airway resistance. Okay, your airway can become compromised. Not that your lungs are perfectly fine, but if you can't get air into your lungs, that's a problem. So think asthma. Okay, and last, CNS depression, alcohol poisoning, drug overdose, where you're simply not breathing. Okay. Okay. So alveolar lung exchange is influenced by oxygen release of alveoli, and that's defined as this thing right here, composition of inspired air and alveolar ventilation. Okay. Alveolar gas exchange is also influenced by surface area, diffusion distance, okay, and the adequate perfusion of the alveoli. We'll talk about each of those later. Okay, diffusion rate. Okay, is correlated with surface area times gradient concentration times mirror permeability. Okay, diffusion rate is equivalent to 1 over square of the distance. Okay, so if you double the distance, you decrease the diffusion rate by 4. Okay, so here's diffusion rate. Okay, so one of the reasons why we tell you in anatomy simple squamous is really important in lungs, because the thicker it is, the more the diffusion rate slows down. Okay, every little bit, okay, decreases the rate of diffusion by a lot. Okay. Okay, so diffusion problems cause most of hypoxia. Okay, so it's not the only way to cause hypoxia, but it's by far the most common way to cause hypoxia. Okay, so diffusion rate is roughly 1 over distance squared. Okay, so pathological changes that adversely affect gas exchange, surface area, diffusion permeability, diffusion distance. Okay, so let's take a look at all these cases. Okay, so this is normal. Okay, this is emphysema. Emphysema, you have less surface area. Less surface area, less diffusion. Okay, so while your oxygen levels inside the alveoli are normal, there's not enough surface area to transfer the oxygen into your blood vessels. Okay, fibrotic lung disease. Okay, fibrotic lung disease affects breathing rate in gas exchange in 2 different ways, not breathing rate, but gas exchange. Okay, one, this here is fibrotic, so it's thicker than normal. It's thicker than normal, then it's harder for the oxygen to cross and get into the blood supply. Okay, 2, fibrotic lung disease means you have a lot of fibers and stuff in your lungs, which makes it harder for your lungs to stretch open. And if it's harder to open, then it's harder to get air in. Okay, so that's the loss of lung compliance. Okay, so this can either be normal or low. Okay, the next one, pulmonary edema. Okay, fluid in the interstitial space increases the diffusion distance. Okay, this is what's killing people in COVID. Okay, they can't breathe, and they lose consciousness because they don't have enough oxygen. Okay, so PO2 is normal. The breathing into the lung is normal, but since the diffusion, there's so much fluid in here that the distance is abnormal, is dramatically increased, and therefore the amount of oxygen that enters the bloodstream is much lower than normal. Okay. Asthma is airway resistance. Airway resistance. This is all normal or low, but this is actually low. This is because the bronchioles are restricted, and therefore you can't get oxygen into the alveoli. If you can't get oxygen into the alveoli in the first place, then you have no way of getting into the blood vessels. Okay. So make sure you understand these 5 or 4 cases. Okay. The 5th one's normal, which I'm sure you guys know. Okay. All right. Okay. So those other slides are basic physics. Okay. Gas transport in the blood. Okay. Gas transport is you have 2 components: oxygen and carbon dioxide. Okay. So let's talk oxygen first. Oxygen. Okay. First dissolves in the plasma, but as soon as it dissolves in the plasma, most of the oxygen actually gets sucked up by hemoglobin. Okay, so hemoglobin, okay, binds okay, so when the partial pressure of oxygen goes up, this shifts to the right, which then binds more hemoglobin to oxygen. When the partial pressure of oxygen goes down, it shifts to the left, and you release hemoglobin in stuff. Okay, so when you are breathing in, your lungs are full of oxygen, so the partial pressure of oxygen goes up, and therefore the hemoglobin binds to oxygen. In the tissues, okay, there's less partial pressure of oxygen, so oxygen is released from the hemoglobin. Okay, and that is the way hemoglobin actually works. Okay. Okay. So, okay. So, okay. So oxygen binding is expressed as percentage saturation of hemoglobin, and you can measure that. Okay. So saturation curve. So let's take a look. Okay. So most of the oxygen, 98% of oxygen, is actually transported by hemoglobin. Okay. One of the cool things you should know that this is true if it's arterial blood. Okay. Normally, but if you put on those oxygen, if you carry around one's oxygen container and stuff, and you're pushing pure oxygen into your airway, the pure oxygen, because this saturates at 98%, more oxygen can actually enter into your plasma. Okay. Okay. So this is what your oxygen levels would look like if it was just if you had no red blood cells. Okay, you would just have oxygen dissolving in the plasma. That's not a lot. Here, okay, you have oxygen dissolving in the plasma and the hemoglobin. Okay, so hemoglobin will suck it up, and then more will dissolve into the plasma, and the hemoglobin will suck it up, and more will dissolve into the plasma. Okay. All right, so let's watch the video.
In this video, we are going to look at the role that hemoglobin plays in determining how much oxygen can be transported in the blood. Without hemoglobin present, cells cannot get enough oxygen to stay alive. Blood has two main components, the liquid portion known as plasma, and the red and white blood cells. Plasma contains dissolved oxygen, indicated by the PO2 of the plasma. Red blood cells carry oxygen on the iron-containing pigment called hemoglobin. In a normal person, more than 98% of the oxygen carried in blood is found bound to hemoglobin. This box diagram represents the four compartments involved in oxygen transport. It is useful for understanding the cause-effect relationships among the different aspects of gas exchange and transport. The composition of the atmosphere and alveolar ventilation determine the oxygen partial pressure, or PO2, of the alveoli. As long as gas exchange in the alveoli and alveolar blood flow are normal, the PO2 of the alveoli will determine the PO2 of systemic arterial plasma. The PO2 of the plasma, in turn, determines the percent saturation of hemoglobin. Percent saturation of hemoglobin refers to how many of hemoglobin's binding sites are carrying oxygen. The relationship between PO2 and percent saturation is typically illustrated with this graph. From the graph, you can see that a typical alveolar PO2 of 100 millimeters of mercury Hemoglobin is nearly 100% saturated. At the PO2 of a resting cell, about 40 millimeters of mercury, hemoglobin is about 75% saturated. Percent saturation, however, cannot tell you how much oxygen is being carried in the blood. Total oxygen transport depends not only on the PO2 and percent saturation, but also on how much hemoglobin is present. For example, when hemoglobin is 100% saturated, 1 gram of hemoglobin can carry 1.34 milliliters of oxygen. How much oxygen can half a gram of hemoglobin carry if it's 100% saturated? The answer is half as much, or 0.67 milliliters of oxygen can be carried on 1/2 gram of hemoglobin. Here's another problem to work. Suppose a person has no hemoglobin in his blood, as shown in the box diagram below. What will happen to the amount of oxygen that can dissolve in his plasma? The answer is nothing. The alveolar PO2 is going to be the determining factor for the amount of oxygen that dissolves in plasma, indicated by the PO2 of the plasma. This is true whether or not there is hemoglobin available in the red blood cells to take additional oxygen out of the plasma. Now we're going to look at the role that both percent saturation and amount of hemoglobin play in influencing oxygen transport. For this example, we will simplify and assume that at a PO2 of 100 millimeters of mercury, hemoglobin is 100% saturated. That is, all 4 binding sites on a hemoglobin molecule are bound to oxygen. As we add more hemoglobin molecules, the amount of oxygen being transported increases. In our example, 5 hemoglobin molecules then can carry 20 oxygen molecules. Now let's see what happens if we decrease the PO2 and therefore decrease the percent saturation of hemoglobin. We will choose a PO2 of 28 millimeters of mercury, as this is the PO2 at which hemoglobin is only 50% saturated. We see this with our hemoglobin molecule carrying only 2 out of a possible 4 oxygens. If we use our same 5 hemoglobin molecules, we see that we are now carrying half as much oxygen, or 10 oxygens on 5 hemoglobins. To restore the oxygen carrying capacity of the blood, the body must make more hemoglobin. This is exactly what happens when people ascend to high altitude where atmospheric oxygen content is low. Within days of coming to high altitude, the body begins to make more hemoglobin to carry more oxygen. In summary, the total amount of oxygen that is carried in the blood is equal to the amount dissolved in the plasma plus the amount carried on hemoglobin. The amount carried on hemoglobin depends both on the hemoglobin content of the blood, but also on the percent saturation of the available binding sites. Percent saturation of hemoglobin, as you've learned in this video, is determined by the PO2 of the plasma.
Oops. Okay. Okay. Sorry, I thought it was a little bit. All right. That other screen. Okay. Okay. So things I can change. Oxygen hemoglobin binding levels. Okay. Okay. So shift to the right. So lower pH, increased temperature, increased CO2. Okay. Shift to the right. More decreased infinity, more O2 released. Okay. So when you exercise, right? When your body's exercising, you increase body temperature. You increase body temperature, that the oxygen goes to your tissues. Okay. When you exercise, you also produce lactic acid. Lactic acid lowers the pH. More oxygen is released to your tissues. Okay. When you exercise, also, okay, you increase CO2 levels, right? CO2 levels lead to a decrease in O2 affinity. More oxygen goes to your tissues. Okay, and the same thing shift to, like, all these are exact opposite, right? Okay, so the Bohr effect is a shift in hemoglobin body saturation curve resulting from a pH change. Okay, so we have this molecule called 2,3-bisphosphoglycerate, or 2,3-BPG. It shifts the saturation curve to the right, and if you're chronically hypoxic, then you want to make more 2,3-BPG because you want to release more oxygen into the bloodstream. Okay, if you're currently low oxygen, then you want to release more from the hemoglobin. So okay, chronic hypoxia results in 2,3-BPG. Okay. Okay. So here is the saturation curve. Okay. Here, this is really cool. Okay, this is a normal resting human. So this is the maternal. If you have babies, okay, the shift, okay, is this way, right? So what happens is the fetal hemoglobin is better at capturing oxygen and holding on to oxygen than the mother. So if the mother, so there's a place, okay, in the chorionic villi where these two red blood cells are right next to each other. They don't cross, but they're right next to each other. And the fetal red blood cell always wins and captures the oxygen from the mother. So that forces the mother to give up the O2 to the baby. Okay. Okay. So affect the pH, affect the temperature, affect the CO2, all that increase in pH, temperature, and CO2 pushes it to the right. Okay. Maternal the fetal hemoglobin pushes it to the left. Okay. All right. Okay. The next thing that we want to talk about is carbon dioxide. Okay. Carbon dioxide is transported in 3 separate ways. Okay. Dissolved in plasma, diffuses into our red blood cells. Okay. And then in the red blood cell is either bound to hemoglobin, which is 23%, or most importantly, converted to bicarbonate, and that's 70%. Okay. CO2 and bicarbonate ions. Okay. This is bicarbonate anhydrase. There's a chloride shift. It exchanges the bicarbonate for Cl to maintain electron negativity, neutrality, so it doesn't become all negative charges. Okay. All right. Okay. So this happens. Okay. Hemoglobin H plus result in respiratory acidosis. We'll talk more about that in a couple of slides. But for now, okay, hemoglobin and CO2 can combine to form carbanoaminohemoglobin, and then this reverses in the lungs. Okay. All right, so here, okay, CO2 diffuses into the cells and into the systemic capillaries. Some of it stays dissolved, most of it goes into the red blood cell. In the red blood cell, it gets converted, 23% is held by the hemoglobin, that's fine. Some of it has to be pumped out though. So water plus CO2 goes with carbonic anhydrase, goes to form HCO3 minus. This is pumped out and chloride is pumped in to remain neutral. Okay. So the additional H combined with hemoglobin. Okay. So that's right there, chloride. So H is here, Cl is there. So chloride. So this will make this thing more acidic. Okay. Okay. When there's too much of this, it turns into acidosis. Okay. All right. In the lungs, okay, the opposite occurs. It gets converted back to CO2, and CO2 can exit in the alveoli. Okay. Okay. So the next important thing is control regulation. Okay. So here's the control regulation. Okay. Well, you gotta realize, okay, the control regulation really is a control, okay, here, okay, that's CO2, 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 okay. In the peripheral chemoreceptors in the blood vessels, you can measure O2, you measure pH, you measure CO2, but the predominant one is actually CO2. Okay, oxygen must fall below 60 millimeters of mercury to trigger reflex. That's really, really hard to do. That's not normal. Okay. Okay. So I just had a little break to check something, but so oxygen must fall below 60 millimeters of mercury. That almost never happens. The average is from 175. So to go all the way down to 60 is pretty dramatic. Okay. But we actually measure CO2 levels. Okay. The chemoreceptors respond to changes in CO2 levels. Okay. So CO2 is converted into bicarbonate H plus. Then you measure the amount of H plus, and that correlates to the amount of CO2. And so we breathe when we sense our CO levels are too high. Okay, not oxygen levels. Okay. Okay. So the carotid body, in the carotids, they have O2 sensors. Okay, that cause ventilation. Okay, the central brain measures CO2 in cerebral spinal fluid, and that's here. Okay. All right. So, again, this is all in the lower brain center. So, like I told you guys in anatomy, this is all controlled by the brainstem, so the pons and the medulla oblongata. Okay. All right. Okay. All right, that's it for this chapter.